So let's get started. Summary, week 6. So we had introduced the mean field theory approach, and then used this to, for the first time actually, derive critical exponents within the framework of mean field theory. And so as first derivative of the free energy, we looked at the magnetization, denoted S following Yeomans or small m, lots of other notations, and it scales with the reduced temperature to the power 1/2, which means that the magnetization is also the order parameter, distinguishing different phases from each other. And so the critical exponent here is the beta 1/2. Similarly, we can look at the magnetization as it scales with the applied field, and that's a factor 1/3. So what we have here is this kind of relationship, and this identifies the critical exponent delta to be 3. And then we looked at the second order derivatives of the free energy, like the susceptibility, which we found to be to diverge at the critical temperature. So this is Tc, this Xi, C, okay, not well drawn. And that's also known as the Curie-Weiss law, and tells us that the exponent of the reduced temperature as 1. And so you can see that these critical exponents are defined as 1 over delta, in this case, to the power of beta, and here minus gamma, right? So this goes back to their definitions. And similarly for the specific heat, we observe a jump in the specific heat, and find this exponent to be 0. Last, we derived the Helmholtz energy to read and so we saw that this is a quadratic, a 4th order polynomial in the magnetization. So looking at the states of that minimize the free energy, we find that what is determining the shape of the free energy is this, like this is always positive, but this can change sign depending if T is above positive or below the critical temperature, negative. And so for below the critical temperature, we find this Mexican hat shape of the free energy, and see that there are 2 minima, one at minus m0, one at plus m0, and so both states are possible, and we expect spontaneous magnetization based off this free energy landscapes. But we also expect, since they both have the same minima, to observe domains of magnetization that are either minus m naught, m naught, that shrink in size or grow, like, you know, the ratio of them then grows to this entire system as we go down with the temperature, right? So the magnetization that I can read off here is the proportion of this number of spins in the minus m naught states and the number of spins in the m naught states. And as I flip this proportion to be entirely in this state or in that state, I achieve full magnetization at 0 temperature. And then we opened up a short discussion on why power laws are scale-free. So power laws, I refer to this kind of function. You have a rescale variable to the power of an exponent, and you saw that phenomena obeying power law look the same no matter at which scale we probe them. And so how do we, how can we have these power laws governing a process? Well, since it's independent of which scales we probe the system in, so like if this is a spatial function, so I have to find the same law for, say, spins 10 sides apart as it's 1,000 sides apart. And so if you imagine like spins being following the same relationship that are 1,000 spins sides apart, then you have to have long-range correlations. So it's a hallmark of long-range correlations that gives rise to these scale invariance or scale-free systems. And then we derived the correlation mean field correlation function to find that the correlations obey minus square root of the reduced temperature R. And if we identify this with the expected behavior of an exponential decay driven by the correlation length, then we identify this correlation length to be T2 minus half, which gives us the last critical component of nu being half. And so that closed mean field theory approach, where we derived really a model where we could all of a sudden calculate the critical exponents based on this variational approach. But this variational approach that appears that, you know, you have to be really lucky to find a good non-interacting Hamiltonian that you can explicitly solve for, and you never know how good your variational description actually also is. And so in the effort to put this on a more solid footing, we started looking into the Landau-Ginzburg theory, which we're going to continue today. So the idea here is that we coarse grain a system's microscopic properties to arrive at an effective Hamiltonian that's describing the system. And so actually today I will continue this phenomenological approach of how to arrive at a Hamiltonian, but then for the Ising model, we're actually gonna bottom up coarse grain to see that the symmetry-based Hamiltonian that we make as an instance is not, is very well rooted in the approach of coarse graining, even though it's a clumsy mathematical approach. So the idea is that my effective Hamiltonian is now a function of a field variable, so the magnetization as a field, and we describe this as minus a logarithm of a weight function that's weighing, drawing the weight of the individual magnetization configurations, where now the partition function as a function of temperature is this is the integration of over the states, and this would be the corresponding weights of field configurations. Oops. And this is the integrating over all field configurations. And so the phenomenological whereas the coarse graining, that would be the bottom up. We made assumptions, or like we know that the system obeys physical laws, right? And so we can actually just meticulously go through it. What do we know about the system and how does it constrain our effective Hamiltonian? And so what we looked at so far is concept of locality, which tells me that I can write this summation over field configurations as an integration over, say, an energy density. As all individual parts are independent. So I can write as energy density. So my beta H then becomes product over integration over states of there we go. Then we can have a uniform system that we look at that tells us there's no explicit dependence on X. We had the concept of analyticity, which tells us that this effective Hamiltonian can be expanded, say, as a analytic function, which we can always approximate as a polynomial. And last, we started out looking at the symmetry of a system. Say we have rotational symmetry. Then the effective Hamiltonian needs to be invariant over rotations of the magnetic field. And that tells us that we can't have linear terms in the magnetization because that would render them not, depending on the orientation of the system. So the lowest order term would be the square of the magnetization magnetic field to lowest order. And so now we continue here by starting into the days. Oops, and so first let's phenomenological continued. So symmetries, we so far only considered rotational symmetry, but we could also have an isotropic system, which means that all directions of the systems are equivalent. So like there's no preferred lattice orientation of my spin lattice that I consider. So that means that also rotation applies to the gradient of the magnetization field. The Hamiltonian needs to be invariant under, so that needs to be the same as this. And so again, as previously with the rotational symmetry, that tells us that the lowest order I can have for these divergences of the magnetic of the field, they need to be of squared order to lowest order. So I need to use, more generally speaking, combinations of derivatives that are invariant under spatial rotations. And so the simplest term would then be square, which in Einstein, which actually means that I'm summing over all and all dimensions, alpha equal 1 to d, and then I have derivatives in all directions of the different spin magnetization fields. And here, just to familiarize you with this notation, what this here means is a partial derivative along the alpha space direction. So that would be the simplest term. I can also consider higher order terms, like obviously this Gaussian of the magnetization field, where we then have double derivatives. So I'm not only summing over the field states, but also have two sums. Purpose here is really mainly to make you, the alpha familiar with this notation, because we're gonna start using it pretty soon. Or I can have also mixed terms of the magnetization in its derivatives. so another, so there's a squared, let's didn't make it here. And for example, these kind of terms, which would then read I have an mi, and then the alpha mj, the alpha mj.
Question?
Yes.
Shouldn't M also have D components, or why do we only have what's the N standing for? Normally, when I write nabla M like vector, then it's just a divergence. And this is, I mean, okay, this is a different notation, sure, but I thought that
It's on the of your magnetic field has less than. Yeah. So like in general, I would say N is equal to D,
okay.
but for the general, like for being in general in my notation, I don't make an assumption here.
Oh, okay.
And this is what this would be the typical application that you consider.
Mm-hmm.
And so now we already constrained this quite a bit, right? So we said that we're having a polynomial expansion. We have as lower order term magnetization field squared, derivative of the magnetization field squared. We could have in principle components, and we have a polynomial expansion. And so as we shall see in a few moments, that the magnetic for magnetic systems, we can write down the Landau-Ginzburg Hamiltonian as the following. In few, okay, maybe few pages. It's sufficient for magnetic systems to define this effective Hamiltonian as a constant, and then integrating over all spatial dimensions. And then here we have t a half m squared of x u m to the power 4. And a spatial derivative term. In principle, there could be higher components here, and then the applied magnetic field. So this is basically considering only the lowest order components. Why should this look familiar to you? Compared to, we can compare this to the mean field result, where better mean field was given by, let me just restructure, minus ln2 plus t over a half m squared plus a 12th tc over t m to the power 4 minus mh. So you easily recognize that this structure, which now arose from entirely different parameters, right? So this mean field Hamiltonian will arrive from a variational approach, whereas here we started with symmetries, properties of the systems to write down which terms are actually possible, and just recognize, looking at the lowest order. So we identify a constant contribution, which we typically neglect because it doesn't, it's just renormalizing the energy of the system. Quadratic contribution, a quartic, and the applied field. And here are terms that consider really the long-range interaction, which we obviously had neglected because we just in the mean field approach described the field just as the mean field of the neighbors. One thing that you should take from this comparison is that with this phenomenological approach, as the same idea of exponents, what we gain is that it's very straightforward to write down a Hamiltonian. What we lose is the insight into the microscopic nature of these parameters that are governing our Hamiltonian. And so by no means do all these parameters scale with 1 over kBt, right? There's a 1 over kBt up here. We don't know this, right? So these parameters may very well depend on temperature, for example. So there are system-specific characteristics that are hidden in these parameters. And so this is what you can nicely see from this comparison, that this U can have a temperature dependence. And that's due to this coarse graining effect. So note, not all terms are better, may be dependent on system characteristics and temperature. Due to and then just to make this comment also, this is the magnetic work of an applied magnetic field. And also to note potential higher order terms would be m squared m h, for example, also to be considered. Now that we look at this Hamiltonian, we can also push a little further our physical intuition of what we already know about the system regarding the sign of these parameters, for example. Because we require the system to be stable. What does it mean to be stable? Like, for example, I don't want the Hamiltonian to diverge as I send my magnetization to infinity, for example. So it needs to be bounded. So field theory. So so we know, for example, that the weight, of the field needs to be finite for m to infinity. And as we can think of m, or m is defined as e to the minus beta of my effective Hamiltonian, we can see that the highest order power needs to be a positive coefficient so that the weight decays to 0. So the highest order power m as a positive coefficient. So the U. in this case, right? And just another note, which is not really of importance here, but we also need to be careful regarding gradient terms, because they may generate oscillatory instabilities. So we also need to check signs here. Okay, so this defines now a Hamiltonian. And just to finish like the general setup, just a few words on the integration over states that we generally do here. So now that we have our effective Hamiltonian stated, partition function then reads is now a functional integral over field configuration e to the minus beta of this effective Hamiltonian. Functional. What I can basically, what I have here is integral over the free energy, which depends on the field itself and gradients of the field and so on. And I can look at these integration of the magnetization of the fields also in the framework of coarse graining from lattice points, where this would be defined as sending the number of lattice sides n to infinity, and this would be a product over all lattice states, and this is the same f, except now that we would define this as ni, not dimension, but the lattice sides, and this being fm I alpha mi alpha plus 1 minus mi alpha over lattice side. Yeah. We need this because now we want to derive the effective Hamiltonian for the Ising model in a bottom-up approach. So we start with the Ising model, and then we're going to do this coarse graining to see which Hamiltonian we arrive at. So it's the next topic, the derivation of the Landau-Ginzburg that I already gave. Hamiltonian in for the Ising model is being important. Okay, so to derive the Landau-Ginzburg Hamiltonian, I'm going to first introduce you to the Hubert-Stratonovich transformation, which allows us to reorganize our partition function. So so what we do here is the same as let's derive a field theory the Ising model. And so first we derive some useful transformations. And the starting point is that I want to show that e to the power of a half k s squared is the same as a constant. There is no function of s times an integral over space over a field exponent 1 over k psi squared plus psi s. You will see why these relationships, transformations will become useful later on. But let's derive this. And to see that this is actually true, let's start by looking at the right-hand side. Oops. In the exponent, what we have there is a half k minus 1 psi squared plus psi s, which I can also write as minus a half k minus 1 psi minus k s plus a half k s squared. Exactly. So and now let's define psi dash as psi minus ks, so that we describe can write the right-hand side of the above. Let me just put my notation here. Minus 1 psi squared plus psi s as now an integral over d psi prime. Now we have a half k minus, now we have this psi prime plus a half k s squared. And so this now doesn't depend on psi, so we can move it out. So that's then e to the power of half k s squared r psi prime minus a half k prime psi prime. Sorry, the squared. Oops. Ah, sorry, and that's got lost in there too. And so no, that's a closing bracket too many. This bracket. Okay, so now we just did this, like we expanded the square, and we renamed, changed the variable. So what we arrive here then is just a constant. That's a constant here that doesn't depend on s, and this exponential. So this is constant, i.e. no function of s. So I have a constant times e to the half k s squared. So now we can identify that this is the factor on the left-hand side, this is a constant, and this is what we have on the right-hand side. So this is the essence of the Hubbard-Stratonovich transformation, except that for now, I only looked at scalar variables, and in principle, we have vectorial variables. And so in this, and its full length, then the Hubbard-Stratonovich transformation then reads that I have now on the left-hand side a half J S I K A J S J, and that's then also constant. And now I'm integrating over the field configurations of all spin sides. This is what's going to be. And here we have then a half, again, a summation ij 1 to n, psi I k I j minus 1 psi j rounding out of space plus psi I s j, psi I s I, oops. Okay, and for this, then the proof goes analogously, that we start with the right-hand side. So the idea is already sketched for the scalar system, where we only consider basically one spin above. But if we start now with this right-hand side, where we have all spins on lattice considered, Kij minus 1 psi j. I can already do the same rescaling as before, minus ks. So if I do this, then what I have here is psi I minus sum over L, k I L S L times k I j minus 1 times psi j minus L k j L S L. And now we do this. I know that I'm now also rescaling minus L K I L S L. I becomes I prime Kij minus 1 psi j prime, which is again independent of all spins. And so again, what I left out here now is this term, which would still be dragging on the spin dependence and would be the prefactor in the end popping up on the left, right? And now we can rearrange the right-hand side that we assumed here to see that what we had there written down was the following terms: L, O, L, K, A, L, S, L, J, minus 1, J. And this is nothing else if we work it out as psi I k I j minus 1 psi j plus summing over the product of these terms together. So what happens if I multiply kaj minus 1 with kjl, and I'm summing over j, what I get is that there's only one contribution for delta jl, and so that's why this product of this term, and this term times this, then provides me with psi I s psi. So it becomes sorry. I sum over j, and so what's left is a delta IL, and delta IL then makes the SL into an SI. So what I'm left is the summation over I, psi I SI. And of those terms, I have two because I have the product with this and this, and the product with this and this. And what's left then is the product of that, and that gives me minus a half sum I j s I k I j s j. There we go. And so analogous as, maybe I should state this, that the sum over j of kij minus 1 kjl is delta IL. So this is the only rule that we have to use to arrive at this equation. So analogous as above, we find the Hubbard Stratonovich transformation. Okay, so we can do it, right? So this is the transformation that we can now do. And so why do I want to do this? Yeah.
C prime doesn't depend of S, like of this P.
Yeah, so what we're doing here, and so that's the analogy to the mean field theory again. So we are here looking at the psi as our magnetization field, or will be our magnetization field, right? And so what we're doing here is we're summing over the average, we're looking at the variation of the magnetic field relative to the average spin. So the average magnetization. So in the essence, without ad hoc assuming this answers there's a mean that I can describe the system as a mean field, but rather, which we did in mean field theory, what I do now with the coarse graining is that I make use of a mathematical transformation to translate my to change my sum over states, and thereby sort of arrive that the useful transformation is to describe the mean, the magnetization as a mean field. So this transformation kind of arrives from mathematical terms, but it has the same meaning. And so it doesn't depend on the individual states anymore, right? It's an average quantity because I'm summing over all states. So it's the overall magnetization of this system, and doesn't explicitly depend on the individual values anymore. Okay, so now we have these tools, and so we can now turn to the partition function of the Ising model again. So what we have is that the sorry, why is that? It's a comma. Sorry, that T And again, I'm making this ansatz that my applied field depends on, I'm starting with the most general formulation where my applied field could be different for individual spins. Then it's the sum over all states. X half AJ, K IJ SI SJ. But now the K is J over beta T, beta J, sorry. Plus I HI SI. So here, sorry, J IJ beta is KIJ and oops, beta HI is small hi. And so here we don't restrict ourselves. So okay, so I popped in a factor of a half because I don't want to take I don't want to sum over the bonds, like of I being neighbor to J, because if I is neighbor of J, J is neighbor of I. So I always sum twice over the spin states, so I'm normalizing by a factor of 2. So this here is since I is neighbor of J, so is J of I normalized by. Okay, and so now we're just going to pull out this mathematical trick to describe this as a integration over field variables by using the Hubbard-Stratton-Rich transformation. This then writes so now we're just gonna use what is it here, right? This becomes this term on the right hand side. Oops. Times a constant times and here we have the sum over this states, going to have an index S, HI minus psi I. Okay, so where are these terms coming from? So this term is this one. And then these two terms, they come from the Hubbard-Stratton-Rich transformation. So it's this term plus this one, and I just separated them out. And so, okay, so why did we do this? Because now we again managed to have the sum over the spin states in only this contribution. And so we can actually, we see that this sum now factorizes into a product of the individual states. So the sum on S are common factors. So we see that this is nothing else but summing over S1 plus minus 1 of X H1 plus, minus plus or minus. Whoops. Oh, there's a plus. Sorry for that. Yeah. Sorry, I know. So we can write so this again, this sum becomes a factor, oops, of factorizes, right? H2 psi 2 S2 and so on. And so each one of this sums is then, if we just solve it for the ice spin, we've seen this before. It's HI plus psi I plus e to the minus HI plus psi I. So it's just 2 cosmos hyperbolicus, oops, HI plus psi I. So the whole sum gives that this product over all, is a product over all cos H, HI, psi I times 2 to the power of n, which I'm gonna rewrite in as 2 to the power of n exponent over the sum again over states of an ln of the cos HI plus psi. And another bracket. Okay, so we dealt with this term, and I'm going to put it back into this partition function so that we have it spelled out. So back into partition function. We then arrive at set t hi is a constant times psi n. And now you see why I transformed it into this exponential description, because now I can write these terms next to each other. And so I have a half I j n psi I k I, oops, j minus 1 psi j, psi j plus a sum over I ln of cos H I plus psi I. And another curly bracket. So this is just rewriting the partition function. You didn't do anything yet. Stay with me for one more just cosmetic rearrangements to just write this partition function a little bit better. So now some cosmetic moves. So we define I as Kij minus 1 psi j. And so this is going to simplify our expression, because remember here that this Kij, right, that's the interaction potential, but it only acts between nearest neighbors, right? So that means that this is equal to K for I and J nearest neighbors, but 0 otherwise. And so that means now if I sum over J of Kij with my new field variable phi I, that means that I have sum over J, and I'm just lumping in this one. And sum over, okay, that was, sorry, sum over I. Sum over I, now definition sum over J, and now we have Kij minus 1, psi J. Yep. Then the sum over J becomes in delta Ij, and so this becomes then, oops. So this becomes a delta Ij times psi J. If I evaluate the sum, gives me a psi I. And so with this in hand, we can write this again as a constant. And oh, sorry, now we have these other fields variables, sorry. Phi 1, d phi n, exponent, and minus a half ij, and this now becomes phi ik ij phi j. Let's see if it fits. Plus sum over I ln of the cosine hyperbolicus of, and now this, oops, sorry. This, we get the sum back in. So we have j k I j I j plus hi, and curly bracket. Okay, so let me loop back to your question before. Why are we doing all these transformations? Because I believe that this transformation is, which is just, you know, a principal cosmetic move. But what you now see is that here you see exactly the term popping up that we had in the mean field theory, right? This is the applied field, and this is the average magnetization of now describing magnetization in field variables. So we basically have this mean field approach popping up again. But I mean, this is the whole the whole game that, you know, I'm going to show you that if I just coarse grain my Ising model on lattices by describing it in field variables, we arrive at an equation and have an effective Hamiltonian that reminds us on the mean field approach that we arrived with a variational approach. Yes.
I'm kind of unsure if this works if Kij is only nearest neighbor because it isn't invertible, the matrix. Yeah, the matrix Kij is not invertible, so our calculation kind of don't work for Kij here.
But but I can
I mean, I only tested it out for n by 3, so n equals 3. So for that, it's not invertible, but it should never be invertible because, like, you have like what, like.
Yeah, no, I know, and I know the answer. I'm just trying to put this in the context of Ising models. So, yes, indeed, this is the KIJ it's an overdetermined system. What the K's describe is my interaction in the interaction energy of my spin system, right? And so what you are, the reason why this is overdetermined is that there's no absolute definition of energy. So we're summing here over energetic states. And so what we can only define is differences in energy, because it's differences in energy that are we can relate to forces and that are driving the physical processes that we observe. But in absolute energy, we can't define, right? That's why, like, we don't care about these constants, because they're meaningless. Yep. They're not a physical process. And so we can still define this inverse, but we have to, like, if we sort of were to implement it numerically or analytically, like, I mean, to solve the inverse of this matrix, what you would do is that you would need to define a reference energy. And so numerically, the way you would do it is you take this matrix, but you take out one lattice point, and then you look at the magnetization relative to this lattice point. And that's a way of how you can define it. You can find other ways to define a reference energy, but that's the physical reason why the system is overdetermined. It has to be, because we're looking at energies. But it doesn't prevent us to do this this math here, because the inverse is still defined if, you know, me being aware that I have to define a relative energy. And the dynamics it describes are definitely there, right? The spins are interacting. And it really just boils down to us not having defined a relative energy. And it's only popping up if you explicitly want to solve the inverse. Yeah. It's the same in flow networks. So it's exactly the same. You have also, like, what you have there in flow networks is that you have interaction between neighboring sites due to and what you define at every at every side, in a sense, is pressures, and the pressure difference is driving the fluid flow, right? But again, what's really physically acting is only pressure differences, and you don't have the absolute pressure. Or take an electric circuit, and then you're talking about the potential, and the total potential is not defined, right? So it's only the differences that are driving it, and it's exactly the same challenge here. Okay, so we see, like, okay, so what is cool about this field theoretic description of the Ising model is that I really want you to note, interesting, like, you know, just doing mathematical transformations, we arrive at a definition that sort of reminds us what we did in this more ad hoc variational approach. And I also want you to note that so far we didn't do any approximations. This is the field theoretic description, the full field theoretic description of the Ising model. Yet, again, we're running into these hyperbolic cosines that we don't like, and we didn't like them in mean field theory. And so what we did is we always did expansions. And here again, we'll do this. So please note, no approximations so far, which means we start now. Okay. So now we're going to start approximations. So first of all, we consider our magnetization field f of xi a smooth function of the lattice coordinates. Xi. And we're interested in the long wavelength form. And so if we're interested in long wavelengths, the trick is to go to the momentum space and expand for k equals small, right? So we go to momentum space. And yet again, I mean, just like really conceptually what we're doing is very, very similar to the phonon case, the very simple case before. Okay, so what we can then do is if we go to momentum space, we define the Fi as IQ xi, these are vectors, and then we have the momentum field. And then we also take into account that Kij is short-ranged. And translation invariant. That means that our Kij really only depends on the absolute distance between lattice sides I and j. Then I can also write my Kij as 1 over n q as a function of xi minus xj to arrive at our interaction strengths in the momentum space. And so with these two definitions, then my term here can be written as, okay, so Iij by Ikij by j is then, note these exponential functions cancel to then arrive at phi q k q minus q. Oops, there we go. Okay, and now we start approximating. So first, we're gonna make an assumption on the interaction strength. We said it's short range, so we assume that this function is we can expand in terms of wave number q here, and remember we are interested in and this is short range, so we get q2. We can expand this, and we basically ignore all the higher order terms. Yeah.
Why is there minus q?
Is there minus?
Oh, maybe I mean, like,
No.
it's a phi q.
Oh, yeah, this is a minus. I'm sorry. I thought here there was a minus, and it was here's no minus. You mean this one? Yeah.
But why?
Because you what you have here. Sorry, let me just make sure that you have this. You have the complex conjugates. That's what I'm trying to exemplify with the minus q.
Oh, okay.
Okay, and then the second approximation that we're going to do is dealing with our stupid ln of hyperbolic cosine that is bugging us all the time. And so if we now expand this is a half x. Okay, this is identical. Minus, oops. 12x to the 4 plus order And so with that, we can then in momentum space write our partition function as let me just abbreviate this integrals. Okay, now we have minus, and now we have no, sorry, I don't want. We have these two terms coming in here, and this gives rise to IQ. Where we here, this is actually we're summing over all terms quadratic in Q or linear. Okay, so that's the first term, and then the second term with the stupid ln cosine, we put in this expansion to arrive at then B naught over okay, so why did I change variables here? Well, because you see that also if we expand this term, we here get a quadratic term, right? The half q's x squared. And so we have quadratic contributions coming in from these terms, which contribute also scale with phi q, phi minus q, right? And so these terms here I subsummed in here already. So some of these, that's why they are not called K0 and K1, because they also depend on these terms here. And that's the quadratic, that's the quartic term. That's the quadratic term, and that's the applied field. And so here we now did simplification. And particularly, we also ignored all higher order terms. So we ignored and that's interested in these long range dynamics. So we ignored phi 6, phi 8, phi 10, but also q squared phi 4, q squared phi 6, and q to the power 4 pi squared, and so on. And so as a final step, we now send the lattice spacing to 0 to really have a field description. Now we send lattice spacing to 0. And so then finally our integration over all field components defined on lattice sides becomes this functional integral over the field states. And also the partition function that was defined becomes a functional, because it's a function of the applied field that in principle can depend on x. which we again gonna just write like that, but we keep in mind that this is functional. And then this becomes, and I'm just gonna write it this way. And we go back to real space, right? So real space, then we see that these linear terms, if we go back to a real space, that's a phi squared contribution, that's a phi to the fourth contribution. And here we have this q term, a q squared term. And so this q squared term, if you go back to real space, that's the spatial derivative, right? So this is where spatial derivative comes up. And so what we have here is then summing over dx of r phi squared plus gradients of phi squared plus u over 12 phi 4 plus, and then this is the field term. And so here now phi represents a field obtained by averaging. Okay. And so what we did here is now we rediscovered the Landau Innsbruck Hamiltonian that, you know, I wrote down before, where we have an effective Hamiltonian that consists of ddx a half, this is just, yeah, multiplying in the half phi squared plus r over 2 squared where we just named phi and magnetization before. The U is not defined, like imagine that they're redefined. The U, it doesn't, we don't know, like we lost all the physical meaning of these prefactors anyway. As I said, like the only thing that we can state about them is the sign, but we don't have a connection now anymore to the interaction strengths between individual lattice sites. But it doesn't matter because we're most likely not able to measure it anyway, and we don't have anything to say about them in a quantitative manner. But if we are interested in this collective dynamics, then I just realized this isn't charging. Sorry, charge, yeah. Okay, sorry. It's we're interested in understanding the collective dynamics at phase transitions, and so it doesn't matter what how these are actually related to the interaction strength between individual spins. And for just as a note, this theory is equivalent to the so-called Euclidean phi 4 theory. And so now next week, because I think it's probably useless to start for the next 5 minutes to dig into yet a new topic. So we then gonna try to make statements about the systems that we describe with these effective Hamiltonians by using the so-called saddle point approximation. The idea of the saddle point approximation is that, again, what we're doing here is, so we have this effective Hamiltonian, which we scroll back to the end of the derivation. Here we go, which defines the weight of the individual field configurations when we sum over all field configurations. And so if we want to do this sum over all field configurations, we expect those to contribute and dominate the state of our system, where the Hamiltonian is extremal. So we gonna look at these states of the system and try to see what they can tell us about the physical properties of the system. Very much like the saddle point approximation that we had in statistical field theory TO4 as well. Except that now we are not, we're always going to deal with our variables going to be fields from now on. So we have this vectorial notation that we keep in mind when we go about. And so that's just change in notation, but that's the idea of the physical concept behind that. If there are no more questions, then this would be it from me today, and I would thank you